In my last video, I showed my rationale behind the formula dy over dx equals c times ex over ey, representing a geodesic on a curved space where ex and ey are the basis vectors of the space varying from point to point. At the very end of the video, I hinted on how I could compute ex and ey in my next video, which I'm about to do right now. I hope you don't mind if Donnie Darko's imaginary friend Frank sits and observes. And while we're at it, I think I'm going to dress like Prince from the Raspberry Beret music video. Suppose we have the surface z equals x cubed plus xy plus y squared. This is a 3D surface. But how can we find functions for ex and ey here, the varying distance vectors between points on the surface? We work with perpendicular cross-sections and use the Pythagorean theorem. In the 3D space, if we move a slight bit dx in the x direction without moving in the y direction at all, we will have to move up a slight bit dz in the z direction in order to figure out the differential distance ex moved across the surface. For instance, we might say that the change in z dz equals the partial derivative 3x squared plus y times the change in x dx. But we don't move across the y direction whatsoever in this cross section. Looking at this closely, we see dx and the partial derivative 3x squared plus y dx as the legs of a right triangle, and the hypotenuse as the infinitesimal distance ex along the cross-section of the surface. To find ex, we now can use the Pythagorean theorem. Formally, this is dx squared plus 3x squared plus y dx squared equals ex squared. But more generally, this is dx squared plus dz over dx times dx squared equals ex squared. Doing some algebra, pulling the dx squared out of the left side and square rooting both sides, we get square root of 1 plus dz over dx squared times dx equals ex. Now that we've found ex, we can use the same process to find ey. And after doing that, we can represent ex over ey in this manner here. Finally, we're making some progress. We can plug this particular value into the equation from the last video. When we do that, we find that we have dy over dx on one side and dx over dy on the other. We can move those to the same side using simple algebra. This may not make much sense here, but I'm going to square both sides to get rid of the radicals simply because I don't like them. Last, I raise both sides to the power of 1/4, and I'm left with a function I believe I can do something with. Now, the reason I did all of this in the first place was to try to plot a surface in Geogebra 3D Online, and then try to plot this equation that I figured was a geodesic in order to verify its accuracy. So I put in the equation z equals 3 times e to the negative x minus 4 squared minus y squared. And I picked this particular equation for a good reason, rather than going back to the earlier example of z equals x cubed plus xy plus y squared that I started with. This particular equation with the e in it puts a little bump on an otherwise flat-looking surface. The formula only requires me to get the partial derivatives dz over dx and dz over dy, which is pretty easy in this case. It's harder to type the formula into Geogebra correctly. Anyway, when I typed in both the surface and the differential equation representing the supposed geodesic, this is the picture that I got. So is this a picture of a surface with a geodesic on the surface? I'm not sure. The line sure looks straight when it's not on a bumpy region of the surface. So it certainly appears to fit the popular definition of a geodesic as being the generalization of a straight line to a non-flat surface. But when I compare it with other videos more legitimate than mine that show what path an inertial geodesic follows on a non-flat surface, I wonder if I'm on the right track. It's really difficult to intuitively picture what an inertial path would look like confined to a non-flat surface unaffected by gravity. It almost makes me want to ask the International Space Station for help in conducting experiments on this. What complicates things is the word geodesic seems to be used for two very different things that happen to be the same thing on certain special surfaces like spheres. Is a geodesic the shortest distance between 2 points? Or is it an inertial path that doesn't bend to the left or right as you go across it? These are not the same thing on surfaces in general. To demonstrate, on this surface here, the path with the shortest distance between points bends sharply when it reaches the obstacle. It is not an inertial path. Shortest global distances and inertial paths aren't the same thing on all surfaces. So which is the proper definition of a geodesic? Which is more of a generalization of a straight line to a curved surface? Do we make a distinction between these types of geodesics by calling them type 1 and type 2 geodesics? Or come up with a new term for one or both types? Heck, maybe there are even more types than two. Maybe there's globally shortest distance and locally shortest distance, and globally inertial and locally inertial. Maybe some of these mean the same thing and maybe not. I would say it makes sense to assign the distinction of a type 1 geodesic to be the kind that follows an inertial path, where as you move a minimal distance, ds, along your path, the ds is always minimized. That nasty geodesic formula that you learn in advanced physics classes will give you a type 1 geodesic. And I would say a type 2 geodesic is the shortest global distance between 2 points. So is the geodesic I have come up with here a type 1, a type 2, or some other totally different type? I believe it is not a type 1 geodesic, because I don't believe the formula I used, dy over dx equals c times ex over ey, is a true inertial geodesic. I came up with this formula so I could graph it, and I had no idea how to graph something that has ds in it. The geodesic equation I attempted to graph here, dy over dx equals c times ex over ey, can be modified to c equals dy times ey over dx times ex. The geodesic equation I used 3 years ago was d over ds dx times ex over ds equals 0. Comparing these, I think for an equation to be a true inertial type 1 geodesic, the equation has to compare dy times ey with ds, or dx times ex with ds. I don't think it works to compare dy times ey with dx times ex for some reason. This is actually pretty shocking to me. I don't think it may be possible to create a reliable formula for a type 2 geodesic, the shortest distance between points. I have no idea where to even start with that. So my guess is this would be a third type of geodesic, a type 3 geodesic, what I would call a step geodesic. When you go one direction a specific distance, and then go in a perpendicular direction a proportion of that distance, and maintain that proportion as you alternate between those two directions indefinitely. One would think this would be inertial, even on a curved surface if the steps are shrunken down enough, but apparently not. It almost seems to me like this Type 3 geodesic is a path drawn on an elastic flat plane, then a distortion takes place on the flat surface where the path has already been drawn. This geodesic shows how the distortion of the elastic plane affects the path already drawn on the plane. I may not have found a way to graph a Type 1 geodesic in Geogebra, as I initially hoped, but I believe I did still find out something helpful to me after all. I found out that there are various ways to generalize a straight line to a curved surface, and I've listed them here in this handy chart. Too bad I only have a way to graph one of them. Again, I find it pretty shocking that Type 1 and Type 3 don't appear to be the same thing. In any case, I hope something in this formula is correct, since I'm not really all that good at advanced math, and I hope that it has some useful value. Then again, maybe I hope it doesn't. I kind of went into recreational theoretical math because I got super bored with applied math in college. But the older I get, the more I don't like new technology. I may use the internet a lot, but I do not use smartphones that much. I hate those darn things because so many people are addicted to them. I mean, they're neat, but they're not that neat. Isn't that right, Frank?
28 days, 6 hours, 42 minutes, 12 seconds. That is when the world will end. And it will end because of these violent and deadly stuffed animals. Otto, Baby Joey, and Zaius.
You're probably right, Frank. Those worthless thugs sure looked vicious to me.